In the previous lecture, you have seen the concept of power supplied by driving force to the oscillator. Now, in terms of the power absorbed by the oscillator from the driving force, we will define a very important quantity which is actually called half bandwidth or simply bandwidth. And in terms of bandwidth, you can discuss in a quantitative manner the important problem of sharpness of resonance or you can say amplitude resonance. And as I have told you earlier that sharpness of resonance depends on two factors. First one is the applied frequency, that is the frequency of the applied driving force, and another is the resistive constant or the damping coefficient. Okay. In fact, when you talk about sharpness of resonance, what does it mean? It means actually sharpness of resonance is a problem of response of the oscillator given to the driving force when the frequency of the driving force varies slowly. How the oscillator gave response to the driving force. This actually deals with the sharpness of resonance. And the response given by the oscillator to the driving force depends on the magnitude of the power it extracts from the driving force each cycle of its oscillation. In fact, you have seen that actually during a resonance, our oscillator derives maximum power from the driving force. And in that very condition, the frequency of the oscillator omega naught, which is its natural frequency, is equal to the frequency of the driving force omega. When omega is equal to omega naught, in fact then resonance takes place, and in this condition the oscillator derives most of the power or maximum power from the driving force. Okay. So now let us see how we can discuss the sharpness of resonance in terms of the power extracted by the oscillator from the driving force. And for this you have to remember the results which we have obtained in my previous lecture. So if you have not watched my video on power calculation by the oscillator from the driving force, which I have already provided you earlier, must go through that video and then watch this video. Okay. And if you have already watched, then you can remember that the time averaged power of the oscillator is given by this very formula. This is F naught square over 2Zm times cos phi. I hope you are acquainted of the quantities used in this expression or in this equation. Here you know F naught is the maximum value of the applied force because the applied periodic force is given by F equal to F naught cos omega t. Okay. So F naught represents the maximum value of the applied periodic force. Okay. And you know this cos phi is called power factor. Okay. And Zm is the well-known mechanical impedance. Okay. Now from the vector diagram which I have shown here, you know when you note down the resistive constant R on real axis, this is your real axis, and this reactance m omega minus k by omega on this imaginary axis. Then Zm, which is the vector impedance of this oscillator, this is represented by this hypotenuse, and this Zm is the sum of R and this I times omega minus k over m. Okay, and from this figure you can see this angle is your phi, and so cos phi from this figure will be given by R over Zm. So now let us substitute the value of the power factor cos phi, which is R over Zm, in this equation at the place of cos phi. So the average power extracted from the driving force by the oscillator is given by F naught square over 2 Zm times R over Zm. Okay, and so this expression becomes F naught square R over 2 Zm square. Okay, but what is the value of Zm, which is magnitude of the complex impedance? You know, this is given by R square plus m omega minus k over omega whole square whole to the power half. But here there is Zm square, so I have not written here power half, because after squaring that half power will cancel out. So the average power is given by F naught square times R over 2 times R square plus m omega minus k over omega whole square. Okay, now let us simplify this expression, particularly RHS of this equation, a little bit, so that you will be able to express this power in terms of the maximum power extracted by the oscillator. Okay, and for this let us take this R square as a common factor in the denominator. So when you will take R square as a common factor, the remaining terms in denominator will be what? This will be simply 1 plus m omega minus m omega naught square. Actually here I have written k equal to m omega naught square, which is well known to you. Okay, and divided by omega and whole to the power r square, because the second term does not contain r square, so you have to divide by r square. Okay, now you can take LCM here, and after taking LCM your result will be m omega square minus m omega naught square and divided by omega r whole square. Okay, and from here now you can take this m square over omega square r square as a common factor, and the remaining term will be omega square minus omega naught square. Okay, so the RHS of this equation now can be written like this. This is F naught square over 2r and divided by 1 plus this much, m omega minus m omega naught square over omega by r whole square. But as I have simplified this second term in denominator, and you have seen this is simply equal to m square over r square omega square times omega square minus omega naught square whole square. Okay, there is a whole square here. Okay, and so you can see, as we have learnt in the previous lecture, that this quantity F naught square over 2r is what? You have seen in my lecture on power calculation by the oscillator from the driving force, that this F naught square over 2r, this is simply the maximum value of the power extracted by the oscillator from the driving force. So instead of F naught square over 2R, I have written here P max. So our final expression for the time averaged power is given by P max over 1 plus m square over r square omega square times omega square minus omega naught square whole square. Okay. So in this way we have expressed the expression for the time averaged power in terms of the maximum power. Okay. Now you can see from this result that when resonance takes place, you know, resonance takes place when the frequency of the applied driving force omega is equal to omega naught. And if you will substitute omega equal to omega naught in this equation 1, what will be your result? After substituting omega equal to omega naught, this second term in the denominator will become 0, and so that this P will be simply equal to P max. So it is obvious that when resonance takes place, our oscillator extracts maximum power from the driving force. Okay? From the driving force. Okay? But if omega is not equal to omega naught, but you vary this omega, then this power extracted by that oscillator will also vary. So you can say that for a given value of R, for a given damping coefficient, for a given resistive constant, by the variation of omega, that is variation of the frequency of the applied force, power extracted by the oscillator also varies. Okay? How this power will vary from from its maximum value when omega will be varied, that have been shown here. You can see in this figure, I have plotted a graph between the power, average power P extracted by the oscillator from the driving force in against of omega for a given value of R, where omega is the frequency of the driving force. As you have seen, when this omega is equal to omega naught, corresponding to this point A, omega is equal to omega naught. And you have seen that when omega is equal to omega naught, then power extracted by the oscillator is maximum. Don't write here A because I have already written A earlier. So say this point is C. This point is C. Okay? And corresponding to this point C, omega is omega naught and P is P max, and which is equal to F naught square divided by 2R, as you have seen. Okay? So when omega is equal to omega naught, then power extracted by the oscillator is maximum. So it is obvious, if omega will deviate from this omega naught, that is either you increases the omega or you decreases the omega, power extracted will be lesser. Okay? And corresponding to this omega naught, there is only one point P corresponding to which the power extracted is maximum. But except this omega naught, whenever you talk about two frequencies, let us say frequency omega 1 and frequency omega 2, you can see corresponding to omega 1 and omega 2, there is same value of P. So now select 2 points on this this frequency response curve. I have considered 2 points on this. This is point A and this is point B. And you can see corresponding to point A, the frequency of the applied force is omega 1, and corresponding to point B, the applied frequency is omega 2, and omega 1 and omega 2 are different. But for these 2 points or these 2 frequencies, power extracted is same. If you consider that the power extracted by the oscillator corresponding to these 2 frequencies omega 1 and omega 2 is just half of the value of the maximum power, if it is so that in that very condition you can say that these points A and B are half power points. It means on the frequency response curves there are 2 points corresponding to which power extracted by the oscillator is half of the maximum power. Actually, such 2 points are called half power points. So in this figure, A and B are half power points. A and B are what? These are half power points. And you can see corresponding to half power points, I have considered that the frequency of the applied periodic force are different and they are omega 1 and omega 2. Okay. Actually, the frequency separation of these half power points is called bandwidth. It is called bandwidth. So what will be the bandwidth in accordance with this figure? In accordance with this figure, you can see the bandwidth will be given by what? Bandwidth, if you denote this bandwidth by delta omega, this will be simply equal to omega 2 minus omega 1. Okay? Omega 2 minus omega 1. This is called bandwidth. Actually, this is the parameter delta omega which is called bandwidth, in terms of which we can discuss the sharpness of resonance. So how we can discuss sharpness? It is easy to see. You can see if this bandwidth will be small, if it is small, then whenever the frequency of the applied force is slightly deviated from this omega naught, there will be a large fall in the power extraction and the resonance will be sharper. Resonance will be sharper. Okay. So you can say when delta omega is small, resonance will be sharp. Okay. And if it is large, not small, then resonance will be flat. Okay. So how we will discuss the sharpness? Before to do that problem, first of all, let us see what will be the value of this bandwidth by substituting the value of this power in this expression, the value of power corresponding to the half power point in this expression 1. We can find the value of omega, that is omega 1 and omega 2, can be obtained by simply using the condition this P equal to P max by 2. Because you know, when this P will be equal to P max divided by 2, then this omega will have actually 2 values. First one will be omega 1 and another will be omega 2, and after getting the values of omega 1 and omega 2, you can easily find the bandwidth. Okay. So let us substitute P max over 2 at the place of P in that equation. Okay. So equation 1 now becomes P max over 2 equal to P max over 1 plus m square over r square omega square times omega minus omega square minus omega naught square whole square. Okay. Now you can see this P max and this P max will cancel out. Okay. And now let us make the cross multiplication, and after that you will get 1 plus m square over r square times omega square times omega square minus omega naught square whole square, that will be equal to 2. Okay, that is equal to 2. Now when you will bring this 1 in RHS, that will be what? 2 minus 1, that will be equal to 1. So you can write m square over r square times omega square minus omega naught square whole square is equal to 1. But you know that this 2b is equal to r by m. You have seen this result from very beginning. So if you want to express this r in terms of the damping coefficient b, r will be simply equal to what? This will be 2mb, and so r square will be 4b square m square. So instead of this r square, I have written here, you can see this is 4b square m square. Okay, and so our final result is m square over 4b square m square omega square times omega square minus omega naught square whole square is equal to 1. Now you can see this m square and this m square will cancel out. Okay, and this omega square minus omega naught square, that will be equal to a square root of 4b square omega square, and that will be equal to plus minus 2b omega. So I have written here, you can see this omega square minus omega naught square is equal to plus minus 2b omega. Now when you will take the term 2b plus minus 2b omega in RHS, in LHS, what will be your result? This will be omega square minus plus 2b omega minus omega naught square equal to 0. Now you can see, when we will take this plus minus sign separately, we will have two equations. So taking the plus sign, we will get one equation which is omega square plus 2b omega minus omega naught square equal to 0. And after taking the negative sign, our equation will be omega square minus 2b omega minus omega naught square equal to 0. So you can see now we have two quadratic equations in terms of omega. Okay, and you know each quadratic equation have actually two roots. So we will have two values of omega from after solving equation 2, and again when you will solve equation 3, again you will get two values of omega. So as a whole there will be 4 values of omega. But when you will solve these two equations, you will see that actually one of the roots of equation 2 and also of equation 3 will be not acceptable, because omega, which is frequency, that can never be negative. But when we will solve these quadratic equations, we will see that one of the roots, that is one of the value of omega, will be negative, which cannot be accepted because frequency is never negative. So solution of equation 2 will give only one acceptable value of omega, and solution of 3 will also give only one acceptable value of omega. So now let us try to solve equation number 2. As you know from the formula of quadratic equation, the roots of this equation 2 will be given as omega equal to minus 2b plus minus root over 4b square minus 4ac, but at the place of a there is 1 and at the place of c there is minus omega naught square. So there will be plus 4 omega naught square. Okay. Now in this equation you can take 2 as a common factor. When you will take 2 as a common factor, there will be minus b plus minus root over b square plus omega naught square and divided by 2. Okay. So this 2 and this 2 will cancel out, and you have omega equal to minus b plus minus root over omega naught square plus b square. Now you can see, taking the plus sign we will have one value of omega, taking the minus sign you will get another value of omega. But when you will take this minus sign, both of the terms will be negative. That is minus b, a minus uh, root over omega naught square plus b square. So as a whole, omega will have a negative value. But as I have told you earlier, that frequency cannot be negative, and so that we will discard that value. We have only acceptable value when we take plus sign here. So the acceptable root of this equation is given by omega 1. Now we denote this omega by the symbol omega 1, and that will be equal to minus b plus root over omega naught square plus b square. Okay. In the similar manner, you can solve this equation 3. Can you solve it or not? Definitely you can solve. But there is a difference between these two equations. Here is minus sign here in second term, and second term was plus here. So when you will solve this equation 3, then you will get that there will be two values of omega, and that value will be equal to omega equal to b plus minus root over omega naught square plus b square. I have not solved it, but you can do it. Okay. Now you can see this second term, which is a square root of omega naught square plus b square, this is greater than b. So when you will take this minus sign, you will subtract a quantity which is greater than this b, and so omega will have a negative value again, and so that value cannot be accepted. And so that the acceptable root of this equation 3 will be what? That will be when you will take positive sign. So the acceptable root of this equation 3, which I have denoted by the symbol omega 2, is given by b plus root over omega naught square plus b square. So in this way you can see we have obtained the two frequencies omega 1 and omega 2, which are the frequencies corresponding to the half power points. Because corresponding to these two frequencies, you can see power is same, and that power is equal to P max over 2. Okay, P max over 2. Okay. And so from the definition of bandwidth, now we can say that the bandwidth delta omega is equal to omega 2 minus omega 1. Now see the expression. When you will subtract omega 1 from this omega 2, the second term inside the square root will cancel out, and this will be b minus minus b, which is equal to 2b. So the bandwidth is simply equal to 2b. Bandwidth is simply equal to 2b. Okay. And in this way we get a simple expression for the bandwidth. And you can see this bandwidth depends completely on the damping coefficient b. Okay. Now as I have told you earlier, when this bandwidth delta omega is large, what does it mean? It means when the frequency gets deviated from omega naught, there is not a large fall in absorbed power, but the absorbed power decreases but slightly decreases. In that condition, resonance is called flat. But if the bandwidth is small, it means due to a smaller variation, a smaller deviation of omega from omega naught, there will be a large fall in power absorption. And in that very condition, we say that resonance is sharper. So you can see this delta omega is a powerful tool to know the nature of resonance. delta omega is smaller, resonance will be sharper. Delta omega is larger, resonance will be flat. Okay. Now the another very important quantity in terms of which we also discuss the sharpness of resonance, that is called quality factor, and it is conventionally denoted by the symbol Q. Actually, you have learned about this quality factor earlier. In present condition, how this quality factor is defined? Actually, in this condition, we define the quality factor Q as a ratio of a resonant frequency over bandwidth. So resonant frequency, which is given by omega naught, and bandwidth, which is delta omega, which is equal to omega 2 minus omega 1, this defines the quality factor. So quality factor can be given by omega naught over delta omega. Okay, omega naught over omega. So you can see this quality factor is inversely proportional to bandwidth. Inversely proportional to bandwidth. And as you have seen that this bandwidth is this bandwidth is equal to 2b. So you can also say that quality factor in this condition is omega naught over 2b. Okay. So if the damping coefficient, if you want to see the variation of this quality factor with damping coefficient, you can say that this Q is inversely proportional to B. Okay. Now you can see if a quality factor is large, when this quality factor will be large? It is obvious from this equation 8. When the damping coefficient B is small, then quality factor will be large. Okay. And Q is large and B is small. In that condition, delta omega will be small. Delta omega will be small. And so the resonance will be sharper. So directly you can say if quality factor is large, resonance is sharper. And when this quality factor is small and B is large, in that condition delta omega will be large. And if delta omega is large, you can say that we have flat resonance. So directly you can say if quality factor is poor, it is small, then resonance is flat. So in nutshell you can say for a high quality we have sharper resonance, but for a poor quality factor we have flat resonance. Okay. So I think after these 3 lectures on the sharpness of amplitude resonance and the concept of a resonance 2, now this problem has been crystal clear in your mind. Okay. So go through all these 3 lectures on the amplitude resonance, and when you will actually attend all these 3 videos on amplitude resonance, each and every concept which may be asked in your examination will be clear to you. Okay. So thank you very much.